Here is an example of the pH calculation of a solution of a salt that is basic. The problem at the top of the page involves finding the pH of a solution of sodium hypochlorite, a compound that is found in chlorine bleach. We'll look at the steps as we go through the problem. First, we need to decide is the compound acidic or basic when it's put in water. Of course, you already know that because I had said this video was about salts that are basic. But if you hadn't known that, how would you decide? The sodium hypochlorite, NaClO, is two ions, sodium ion and hypochlorite ion, the negative ion. Sodium ion is not going to affect the pH. Group 1A elements and 2A elements, when they are in their ion form, do not affect the pH. At least most of the group 2A don't. ClO- is a negative ion, and it's a conjugate base of a weak acid. Those do affect the pH, and they make the solution basic. So that means that we're going to have to write our net ionic equation to produce OH-. So let's do that. Notice it's a net ionic equation. I'm not going to put the sodium ions in here. That's one of the biggest mistakes and biggest causes of problems, is sticking in the sodium ions. They're just a problem. So we'll write our equilibrium with water again. Hypochlorite ion, being negative, will take an H+ from the water to make its conjugate acid. That leaves hydroxide ion, and we have completed our net ionic equation. Now that we have our equilibrium equation, we need an equilibrium constant to go with it. Since we have a base here, we need a Kb. So we need the Kb for ClO-, not sodium hypochlorite. The sodium isn't involved here, just ClO-, but that is not in tables. You will find that the salts, or the ions, are not in tables, only neutral compounds with no charge. In order to get the value from the table, we are going to have to look up the Ka of the conjugate acid and use the equation shown. So you're going to look up the Ka for adding H+ makes it the conjugate acid, hypochlorous acid. The value for hypochlorous acid is 3.5 times 10 to the -8. The Ka will then be plugged in to our equation. And we use our Kw, which is the 1.0 times 10 to the -14th, and end up calculating Kb is equal to 2.86 times 10 to the -7th. I'm going to carry one extra significant figure. This really should be two significant figures. We'll just remember that. Now that we have our equilibrium constant and our reaction equation, let's set up our ice table. The initial concentration of the hypochlorite ion is 0.67 molar, as mentioned in the problem. The other materials are 0 unless they are mentioned. It's assumed that those are 0. Water, of course, is not included, being a pure liquid. You're going to have an increase from 0. You can't have a decrease from 0. So our x's will be added to the products, removed from the reactants, and there we have our equilibrium concentrations. We will put those values, the equilibrium values, in our equilibrium constant expression. So we put the equilibrium values from the ice table into the equilibrium constant expression, and using the K that we have previously calculated. And to make the math easier, we do our usual assumption of saying maybe that x is very small compared to the number it's being subtracted from. So that gives us a much simpler equation to solve. The x squared over 0.67 equals 2.86 times 10 to the minus 7th. It ends up giving you x equals 4.38 times 10 to the minus 4th. Now, is our assumption okay? Yes, it is, because if you see, we had 0.67. If I subtracted 0.0000438 and rounded it off, I would still have 0.67. So our assumption is okay. You could have calculated that it was a less than a 5% error, but these ones where you get a digit that's even further to the right than the last significant figure are easy to just see that it is going to be okay to ignore that x. And last but not least, we have to realize that even though we've solved for x, we aren't finished. What is x? Going back and looking at the ice table, you see that X is not H3O+. This one was forming OH-. This is actually the OH concentration. So we need to calculate pH from that. One easy way is to just take the pOH, which is the negative log of your number, and that gives us our answer 3.36. Now, I'm giving you 2 decimal places because this really was originally a 2 significant figure number. I carried an extra digit. That's pOH. We need pH. pH is going to be 14 minus the pOH, which is our 3.36. So our answer for pH is 10.64. We might look back and say, does that make sense? Because we had a base. Is that basic? Yes, it is. So we made sense. And of course, you can use this method to solve for something other than pH. If you're given the pH value, you can even convert it to H3O+ or the OH- at equilibrium and put that in your ice table to calculate something else, such as Ka or Kb.